Good evening, everyone. We are Group 6, and our topic is ScSIFT and multi-stream fusion plus deep ranking. Uh, these are the contents for our presentation. So, this project addresses the task of image comparison, determining whether two images belong to the same or different class. Image comparison works by extracting feature representation from two images and then measuring their similarity or difference. To do that, we have used two methods, which is multi-stream fusion with deep ranking and ScSIFT with sparse coding. In multi-stream fusion, we combine global features extracted from full images and local features extracted from random patches of the image. These features are generated using the pre-trained resonant 18 model and fused to 1024 dimension representation. In ScSIFT method, we extract SIFT key points from grayscale images and encode them in a learned sparse dictionary, creating 256 dimension feature vector. For the model training, we compute the absolute difference between the two feature models and then train using logical regression model using using the gradient descent. So the data set that we use is tiny image data set, which consists of 200 classes, 500 training images, 50 validation images, 50 test images per class. In total, this gives us 100,000 training images, 10,000 validation images, 10,000 test images. Each image is resized to a resolution of 64 by 64. For the pre-processing steps, we have used Hugging Face to load the data. And the two pre-processing steps that we used are resizing to 64 by 64 and converting them to tensors for scaling pixels between 0 and 1. The feature preparation in multi-stream fusion, we extracted both full images and random patches. And in SIFT, we converted images to grayscale before extracting SIFT descriptors. Neha will speak next.
Hi everyone. So now we are going to discuss the models which we have used in our project. So the first model is ScSIFT, which stands for Sparse Coded Scale Invariant Feature Transform. So it is an image similarity detection algorithm that augments the classic SIFT feature descriptor with sparse coding to improve the matching speed and efficiency. So it can be divided into three stages. The first would be dictionary learning, then the feature encoding and matching. So first we convert the images to grayscale and then we extract the SIFT descriptors, which is of 128 dimensions using the OpenCV. And then we limit to 20 descriptors because 128 is a lot. And we will limit it to 20 per image to control the size. And about the dictionary learning, instead of using the raw SIFT descriptors directly, we sparsely encode them using a learned dictionary. This will capture the key local patterns while compressing and regularizing the information. So while learning a dictionary with 256 atoms, which is 128 dimension each, so the each key point gives us a 128 dimensional descriptor. And then we limit the descriptors. We take a maximum of 20 descriptors per image to control memory and computation. And then using the mini batch dictionary learning, we learn the dictionary. And then each descriptor is encoded using the orthogonal matching pursuit, which is OMP, and it has 5 non-zero coefficients. Next slide, please. So then the offline sparse coding and indexing is in the ScSIFT method. About the feature aggregation, we take the mean pool or a mean of all these sparse codes for an image, and the final feature vector is of a 256D. And about the training, for each image pair, we compute the absolute difference between feature vectors. And about the classifier, we have used the logistic regression model, SCD classifier, with loss equals to log loss. And it has been trained for 100 epochs. And the hyperparameter tuning is same for both the models with the C values 0.01, 0.1, 1, 10, and 100. Next slide, please. So we will not go into much detail about how we have used it in the paper because of time constraint, but about the advantages of ScSIFT. It is a faster matching because it significantly accelerates similarity detection, approximately 52% faster than the traditional SIFT. And it has high accuracy and it maintains and even improves accuracy despite the faster processing. And it has efficient memory usage, which is crucial for large databases. And the learned dictionary representation captures more relevant image features compared to the fixed visual vocabularies. And also the robustness, it performs reliably across various image transformations, for example, blurring, cropping, brightness, adjustments, grayscale. Next, please. Our second method or model is the multi-stream fusion combined with deep ranking. So this method aims to determine if two sets of images show the same object, even when taken from different angles or with different backgrounds. So it addresses the challenge of matching image sets despite viewpoint changes and unordered images, ensuring accurate similarity detection in real-world scenarios. It combines the global information, which is the entire image, and local information, the important patches in it. So this captures both the overall structure and fine-grained details of images. So how it works is the multi-stream fusion extracts both global and local features from images using a pre-trained deep network. And the deep ranking learns to compare image pairs by measuring feature differences instead of the independent classification. So how we have used these in our project is first we have pre-trained the ResNet 18 feature extractor. We have loaded the ResNet 18 pre-trained on ImageNet, and then we remove final fully connected layer with this. And the global feature extraction is when we pass the entire 64 cross 64 image through ResNet 18, which is a 512 dimensional vector. And then the local feature extraction happens, which is by selecting a random 32 cross 32 patch from the image. And then we resize the patch back to 64 cross 64 and then pass it through the ResNet 18, which is a 512 dimensional vector again. Next, please. And then we do the feature fusion. We concatenate the global and local features to a final of 1024D feature vector per image. And then we take the pairwise feature difference. For two images, we compute the absolute difference between their 1024 dimensional feature vectors. And then we run the classifier. We train a logistic regression model, SGD classifier with log loss to predict the similarity. We have used 1 when it's same class and 0 when it's different class. So why this model works, why the fusion plus deep ranking combination improves our matching? Because the global feature captures the entire object structure and the local feature captures the fine local details, that is the textures or small parts. And the deep network features are more abstract and robust than raw pixel or SIFT features. So the ranking-based learning, which is the absolute difference plus the logistic regression, it focuses the model on similarity rather than independent classification, which is more effective for matching. The next slides will be covered by Pragya.
Hi guys. So coming to the second paper, evaluation of multi-stream fusion for multi-view image set comparisons. So the paper addresses how traditional methods only compared single images and it proposed a new method to compare sets of images. It introduced a multi-fusion strategy which had a new set similarity score based on BSS error index. The paper used Stanford car dataset and achieved a 67.7% acceptance rate, a 3% false acceptance rate, outperforming all the base models. We can use this model in fraud detection and visual search engines. Next, please. How can we implement these papers in our code? We had functions like extract SIFT descriptors for the first model and train the dictionary using mini batch dictionary learning. The difference between the sparse coded features are used for training the ScSIFT classifier. In the second paper, we have functions like extract global features which extracts the resonant image embeddings. The difference between the fused features are used for training the fusion later. Next, please. Coming to the hyperparameter tuning, we did manual grid search and then trained each C value for 100 epochs. After training, the result was stored for each C value, which was later chose the best C value with the highest validation accuracy to visualize and plot. The best C for fusion and ScSIFT was chosen separately, and the final model was tuned for higher validation and test performance. The next slides will be explained by Varsha.
I would be covering the testing approach. To evaluate the performance of both models, we conducted exhaustive pairwise testing on the entire test set. Specifically, each test image was paired with itself and every subsequent image in the dataset, generating all unique pairs. And this generated about 12 million unique pairs because there are about 4,900 test images in the dataset. The next slide would be covering the bar chart accuracy comparison for both the models. The This graph compares validation and test accuracy for both models. We initially trained it over a much smaller training set by randomly picking about 1,000 images. And we can see in the first image how it overfits. And the second image is for the entire training data set. Multi-stream fusion consistently outperforms ScSIFT by over 10% across both validation and test sets. And the small gap between validation and test accuracies indicate that both the models generalize well. Fusion's stronger accuracy demonstrates the power of deep features over handcrafted ones. Next slide. We'll be covering the hyperparameter tuning graphs here. This is for the first case where we took the smaller data set, training data set, and we can see it ranges around 98% overfitting for all values of C. Next slide, please. This graph shows how accuracy changes as the regularization strength C in logistic regression is varied. We can see as C increases, both models initially improve with less regularization. It allows better fitting. Accuracy stabilizes near C with the value of 10, indicating an optimal trade-off between underfitting and overfitting. And we can again see Fusion maintains a consistent advantage over ScSIFT across all values of C. Next slide, please. And this is when the best model is used to evaluate the validation and test accuracy. Next slide. The exhaustive evaluation confirms that the multi-stream fusion is superior to ScSIFT in both accuracy and stability. It benefits from deeper, more expressive features and shows strong performance across various regularization settings. And the graphs shown previously support this by clearly demonstrating that Fusion's accuracy edge is better, consistent generalization, and along with the hyperparameter tuning graphs. And that is it. Thank you.